answers.
Hello, ladies and gentlemen. It's my honor to come here. My name is Chen. This is my partner, Kame Wang. We are come from Tencent General Lab. Our topic is security analysis on the attack surfaces of blockchain client. First of all, let me introduce myself. I am a security researcher. My research mainly focuses on the security of blockchain, Windows kernel, and virtualization.
Hi, I am Kim Wang. I am a PhD of Chinese Academy of Sciences. My research interests include blockchain security, automatic code analysis and test, and mobile security. I used to be a speaker on ACM-CCF 2017. It is one of the top 4 academic conferences on InfoSec. Last year, I also made a speech on TSEC conference, which was held in Beijing. We all come from Zhanlu Lab, Tencent Inc. Our leader is one of the most famous hackers from China, whose ID is Yuan Ge. He is extremely good at vulnerability mining and exploiting our Windows system. In the last year, 3 of our researchers are on the MSRC Top 100 list. We are also the winner of Pwn2Own 2017. If you are interested on us, you can find us on Twitter. The agenda of our talk is here. We will firstly introduce the background of our research, and then the attack surfaces of blockchain nodes will be presented. Thirdly, we will show some tricks to find vulnerabilities in these attack surfaces. Some real cases of vulnerabilities will also be presented. In the end, we will make a short conclusion. The nature of blockchain is a distributed ledger on a P2P network. Taking the top public blockchain project as an example, a user's digital concurrency account is a pair of public key and private key. The address of an account is the hash of the public key. If a user wants to make a transaction, he will need to send the transaction message using his private key and broadcast it onto the P2P network. This message will include the account address of the sender and receiver, and the amount of digital concurrencies, and so on. Blocks can be regarded as pages of ledger. Blockchain can be thought like that. These ledger pages are linked together. For public blockchain projects, the generator of new blocks can get a word in the format of digital concurrencies. The process of generating new blocks are called mining. On 2017, represented by Bitcoin, the explosive price rise of the digital concurrencies have attracted a lot of attention and interest on the blockchain technique. Besides public blockchain, which are usually used to issue digital concurrencies, companies are more focused on how to apply blockchain technique on real projects. The financial companies are most interested on this new kind of technique. Furthermore, the cloud service providers are also providing solutions for blockchain network. Many countries are also very supportive for blockchain technique. For example, on June 2015, America released some sweeping new rules for licensing virtual concurrency businesses in New York City. In sharp contrast to the rapid rise of blockchain technique, the security of blockchain ecosystem is very fragile. Various attacks have been reported in recent years. Most direct attacks are targeting owners of digital concurrencies. The wallet clients are the most attractive target. The second type of attacks are targeting on trading platforms. These attacks will result in very serious financial losses. The last attack type is targeting at the blockchain nodes. Some common vulnerabilities may exist in the code of blockchain nodes. Because of the huge amount of nodes, the attacks on these vulnerabilities can result in a large scale of losses. In summary, blockchain is a fast-growing new technique with a rapid range of application. However, its ecosystem is facing attacks from various aspects. Therefore, it is important to study the security of blockchain. Now, let's have a look at the different kinds of attack surfaces of blockchain. The attack surfaces of blockchain network can be divided into three major categories. The first is the RPC interface. RPC is short for the Remote Procedural Call Interface. The second is the P2P interface, which usually contains three main protocols, which are discovery, synchronization, and consensus. The third is a smart contract, whose virtual machine is the main attack surface. Let's have a look at first of all, let's have a look into the RPC interfaces. RPC is a common feature of mainstream blockchain projects. For blockchain node, its core features contain wallet management, concurrency mining, block validation, and P2P communication. While a node is running, it should provide a way to configure functionalities or create some data of the blockchain. RPC interface is the major implementation of this kind of UI. Usually, it is provided in the format of JSON RPC. Taking Ethereum as an example, it has many versions of node programs, which are developed in various languages. The default configurations of these clients only expose their RPC interfaces to localhost. However, the combined address can be configured to public internet address, which will expose their RPC functionalities. As shown in the bottom, it can be done by specifying one argument, which is RPC ADDR. Many blockchain projects will divide their interfaces into different models according to their functions. For example, the RPC models of Ethereum can be divided into ETH, personal, net, miner, and so on. Some models are enabled by default. As shown in the first two boxes, users can create the enabled model list by using RPC models interface. The last box shows that the list can be configured when starting up a node by specifying one argument, which is RPC API. Besides, different client programs may provide their own RPC interfaces and models, such as an Ethereum client named Parity. It is highlighted in red color. In summary, if a node binds its RPC onto its public address, these exposed RPC interfaces will under the threat of remote attackers.
Okay, next is the P2P Discover Attack Service. Firstly, P2P network is different from the traditional CS network. It doesn't have a centralized server. Each of its nodes can be a server or a client. Because the nodes getting in and out of the network is very frequent, nodes in such a network are unable to maintain a full amount of routing information. Therefore, this requires a way to find the target nodes or resource. That is the P2P Discover protocol. Let's take the Ethereum's P2P Discover protocol as an example. It's a protocol based on Kame algorithm. As is shown in the figure, each node keeps a list of seed nodes and a list of neighbor nodes. The seed nodes are fixed, that are maintained alive for a long time. Neighbor nodes are found through the Discover protocol. This protocol is based on UDP and contains 4 types of packets. First, the nodes determine connectivity through ping-pong. Then, send a find node packet with the target ID that you are looking for. Your neighbor then returns a set of nodes closest to the target. Then, you can repeat the process over and over again like a snowball. About the implementation details of the protocol, please refer the source code implementation of Ethereum. Next is P2P synchronization attack surface. The state of nodes in P2P network is very complicated. Some are new nodes, and some are offline nodes, and some have high network delay. So we need the synchronization protocol that all nodes have the same state. In the blockchain system, there are usually 3 types of data synchronization. They are synchronizing blockchain date, broadcasting block date, and broadcasting transaction date. Let's take Ethereum's P2P synchronization protocol as an example. The first is synchronizing blockchain. There are some situations to trigger it. For example, when a new node is added, it will synchronize. When a new block is received, synchronization is triggered. In addition, every 10 seconds, it will positively synchronize. The second is block broadcast. When a new block is mined, it will be broadcasted to the entire network. In addition, when a new block is received, it will also be broadcasted. The third is transaction broadcast. When a new transaction is received, it will be broadcasted to the entire network. When you send a transaction, it will also be broadcasted. This is P2P consensus attack surface. Because the nodes in the blockchain are all equal, each node has the right to general block. So how to determine whose block should be added to the chain? Consensus protocol could solve this problem. Let's take a look at how the Ethereum's consensus solves this problem. Ethereum uses the proof of work consensus protocol. As the name suggests, blocks are selected according to their difficulty, also known as hash rate. The figure is the generation process of the new block. A miner will calculate a hash value, which combines transactions information, block information, hash for the previous block, and the nonce number. This hash is compared with a target value. If the hash value is less than the target value, the mining is successful. Otherwise, the above steps are repeated with another nonce number. When the block is broadcast, the other nodes will validate its difficulty with the target value in order to determine whether to accept it or not. There are a lot of miners in the whole blockchain network. In some cases, a node may receive multiple blocks at the same hit, and both blocks are legal. At this point, the node will select one block according to the difficulty of the block. The difficulty depends on when the block was created, and it also depends on the historical difficulty of the chain. Okay, this is the smart contract interpreting attack surface. Smart contracts are like a SQL script on a database. It is used to implement business logic on the blockchain platform. Its code and data are stored on the blockchain. Usually, a smart contract is a binary array. Just like a Windows PE file, it has its own format. The smart contract creator develops the contract and sends it to the blockchain nodes. It is transmitted on the basis of transaction. Users can also invoke smart contracts by sending transactions to nodes. The blockchain node is responsible for parsing and executing the smart contract. Okay, let's take a look at how the Ethereum interprets smart contract. The figure on the right shows the processing of the smart contract. First, contract developers write source code with script languages, such as Solidity. Then, the source code will be compared to opcode bytes. Next, the bytes are sent to the blockchain network using the transaction. The mining block and the verifying block, it will be deployed. Smart contract is executed in a stack-based virtual machine, also known as EVM. The EVM is responsible for parsing opcode and parsing parameters and performing operations. The left figure lists part of EVM's opcode, such as AND, MAR, SUB, and so on. Because the smart contract and the client are in different execution contexts, so contract can't do client-side operations. Therefore, the client provides some APIs for the smart contract, which is syscall. You can think of it as a wrapper of opcodes. Let's take a look at the ONT's syscall as an example. The figure on the right indicates that it has a syscall opcode. This opcode helps the smart contract developer invoke the various functions provided by the node, such as the functions listed on the left figure. Okay.
After analyzing these attack surfaces, let's talk about how to find vulnerabilities in them. If the RPC interfaces are not protected well, it will result in very serious consequences. Let us learn from a real case. As early as 2016, one researcher claimed that his honeypot has detected remote stealer in the Ethereum network. At the beginning of 2018, this kind of attack got reposted by different groups. Although this kind of attacks have been posted for so many times, the attacks never stop. By now, one of the most famous attackers' account has stolen more than 44,000 ethers, which is the digital concurrency issued by the Ethereum. This account is still receiving stolen ethers from day to day. The stolen ethers are worth more than $5 million. Let's check out how an attacker can steal the ethers from a victim's node remotely. First of all, he will check if the target node's RPC interface is open. If yes, he will try to create the wallet information from the node, and then he will command the node to send all its balance to the attacker's account. The success condition for the third step is that the victim's account should be unlocked to allow the ethers to be sent out. There are two different situations. Situation 1, the attacker knows the password of the victim's account. However, this is very hard to achieve. Situation 2 is that the account is unlocked by its owner. Under this situation, if the account is not relocked manually by the owner, there will be a time window for attackers to invoke the RPC interface to send ethers. Let's make a summary. Ethereum nodes are vulnerable to RPC attacks because that, firstly, they expose their sensitive RPC interfaces and implement no effective caller identity authentication. Secondly, the node programs provide unsafe wallet management, which such like unlocked wallet will leave a time window for transactions. Thirdly, all user nodes are detectable. Otherwise, the attackers could not find a large amount of victims to steal. Based on these three risk factors, let's have a check on this on some other famous blockchain project. Bitcoin has implemented very effective RPC identity authentications. Therefore, it is safe. EOS network is divided into different levels. All the users' nodes are not connecting with each other by P2P protocol. Therefore, even though the other two factors are met, the threat of RPC attacks in the EOS network is very limited. Ripple's RPC interface don't provide wallet management. It only takes care of publishing transaction messages onto the network, which is already signed by users, so that it is safe to. Lastly, NEO is a blockchain project which matches all these three factors. The attacks in its network has already been analyzed by our team, and the details will be discussed later.
Now, let's talk about how to find bugs in code. Also, there are hundreds of blockchain clients. There are few truly independently developed clients. Most are copies and customization of classical projects. You just need to familiar with several well-known clients, such as BTC, ETH, US, and so on. If you want to fast analyze a new blockchain project, there are some different situations. If the project is based on the classical project, easy to get started. You can check it if it has any ND bugs. If it is an independent project, firstly, it is not recommended to read the white paper directly. Just download the source code, compare and run. Secondly, you can use some tricks to quickly find some obvious bugs. Finally, you need to go deep into the code, look at each attack surface, and audit them. Blockchain clients are usually implemented in a variety of languages, such as C++, Go, Java, and so on. The problem with C++ is obvious, since its pointers are prone to memory access errors. Other languages also can cause problems, even without pointers, such as OOM, OOB, and so on. Even a DOS vulnerability can have a big impact on the blockchain, like breaking mining and breaking user transaction. It could even cause 51% of the attacks. There are some common bug situations such as out-of-bound access, integer overflow, type conversion failed, and the map index doesn't exist and not checked. Allocated memory is too large, and rest condition, and so on. Most languages have all the above problems. You could believe that a lot of blockchain code isn't of high quality. They will have many basic errors. So you can summarize some vulnerability patterns for the languages you want to study. Then use the patterns to search the source code directly. You will be pleasantly surprised. Let's make Go languages as an example. I write my own patterns using regular expressions. You can also write more advanced search programs. It might work better. Firstly, this is a pattern of type conversions, such as string conversion and integer conversion. In the Go languages, there is an unsafe type conversion syntax, like the code shown in the figure, which will cause panic. Let's look at an example. This is the result of our search for string type conversions in a blockchain project. As you can see, it uses the unsafe type conversions because the converted value can be controlled by an attacker. It can cause panic. Secondly, this is a pattern of memory allocation. In the Go languages, you can use make to create a dynamic array and initialize its size. If the initial size is too large, it will cause out of memory. The program will exit. This is an example that is the result of a search for memory allocation in a blockchain project. The memory size is controllable by remote attacker, which will result in out of memory. Thirdly, this is a pattern of integer overflow. Integer overflow errors are very common and may have serious consequences. Pattern matching for integer overflow is not easy. It has a lot of matrices and a lot of filtering to do. This is an example that is the result of a search for integer overflow in a blockchain project. End field and origin field can be controlled by attackers. Integer overflow occurs when end is less than the origin. There are some other patterns. First, out of bound access. It often happens when arrays are exceeded. So, this regular expression is used to find the code that associated with the array access. Secondly, inject map index. If there is no index in the map, the extracted result will be empty. If there is code to access it with no checking, it will cause problems. So to find out this problem, first of all, you should get all map objects by find make map, and then check its usage by reference. Many IDE have the ability to find the references. Thirdly, race condition. It often happens in multi-threading. Therefore, we are looking for multi-threaded functions and audit the code of them. We can focus on PEPs, global variables, and other resources shared by multiple threads. Notice that the above patterns are all based on the Go syntax. Different languages have different syntax. You need to write patterns for other languages. If you want to find more vulnerabilities, you need to go deep into the code. It will take more time because you need to understand all kinds of protocols and algorithms. It also has some tricks. You just need to follow the direction of the attack surface. Then you won't get lost in the ocean of code. How to locate the attack surface? Of course, it's certainly possible to read the entire code. However, this is time-consuming. Here, I will give you some quick ways to locate it. Firstly, get the functionalities based on the file names. We are more concerned about P2P, RPC message, and so on. Secondly, we search source code with keywords. Number 1, switch. Many protocols has a switch for parsing. Number 2, send or receive, or server start. These are network-related codes. They are often used by various blockchain protocols. Number 3, message or packets. These are the code associated with the packet or message. Network data is transmitted using them. Number 4, marshal or serialize. Find the code associated with marshal. It is used when network data is sent and received. For example, this is a typical message parsing entry. It contains keywords such as switch, message, and deserialization. When we find these key points, it is much easier to audit around them.
Yeah. Now have a look at how to do vulnerability mining on smart contract virtual machine. We can do further code auditing. The contracts which are developed and called in the blockchain network are all serialized data following certain format. If we can write a wrapper for some certain functionalities such as parsing and interpreting, then it is suitable to do format fuzzing. Of course, code auditing is also suitable in this situation. It requires us to have a deep understanding on the implementation of the entire VM to help locate vulnerable components. This page presents a real case of fuzzing with the FAL on the smart contract runtime of EOF nodes. The EOF nodes implements its smart contract runtime based on two third-party open source projects named WAVM and Binary. I have extracted the wrapper code of WAVM and implemented this one program, which can take a bytecode file as an input to make parsing and interpreting in WAVM. Therefore, this program is suitable to AFL fuzzing. Now, let's have a look at the real cases of vulnerabilities in different attack surface interfaces. In this section, we will analyze some real vulnerabilities in various top blockchain projects like Ethereum, EOS, BTC, NEO, and ONT. First of all, let's have a look at the RPC security problems. There are two projects found to be vulnerable to this kind of problem as introduced in our previous pages. Ethereum is the second blockchain project according to its market value, and NEO is among the top 20. In order to have a comprehensive research on the RPC attacks, we will need to figure out the following three questions. Number 1, how many nodes are vulnerable? Number 2, how serious are the attacks? And number 3, what measures are attackers leveraging? In order to figure out these questions, we have developed an analysis system. It contains a honeypot, victim sniffer, and a node detector. The honeypot will capture malicious RPC requests and find new attack measures from these requests. The victim sniffer will find out the nodes in the blockchain network whose RPC interfaces are exposed. The node detector is a special component which can find all the nodes in the target blockchain network. It is the basic of the other two. First of all, let's have a look at how to implement a node detector. The basic idea is to query all the already known nodes about their neighbor node list. This can be implemented by modifying the source code of nodes or imitating the P2P protocol by ourselves. The effect of this component is that, on one hand, it can make our honeypot easier to be found by attackers if they are deployed on the same network device. On the other hand, it can provide a candidate list for the victim sniffer to find vulnerable nodes. Honeypot is another component in this system. The basic idea is to capture request, craft response, and make record. To ensure the authenticity of the response, we can deploy a normal node for the honeypot to create it. In this way, we only need to craft response for some special interfaces. There are two kinds of special interfaces. The first are the interfaces that can be leveraged to create sensitive state, such like account addresses. The second are those interfaces that have been found to be leveraged by attackers. Victim sniffer is the third component. It is used to find all the vulnerable nodes in the blockchain network. It will take the result of node detector component as a candidate list for testing, which can help to reduce the list size. First of all, it will check if the default RPC port of these candidate nodes are exposed. Furthermore, to find vulnerable nodes that have changed the default RPC port, our sniffer will leverage a very powerful tool named Mascan to get all the exposed port of a candidate node to do further tests. This analysis system is firstly applied on Ethereum. We have deployed 3 test nodes on the Tencent cloud, which located separately at Asia, Europe, and America. The cost of deploying these nodes are not very expensive, which are about $14 one month. The test lasted for one month. The summaries of the test results of different nodes are shown in the second table. If we make a deeper study into the test results, we can conclude three findings. Number 1, the stealing targets contain not only ethers, which are the major digital concurrency issued by Ethereum, but also tokens which are implemented by the smart contract languages of Ethereum. Number 2, victim accounts may under the threat of brute force attack. According to our honeypots, the password dictionary used by attackers contains more than 700 items. Number 3, victims may lose their mining award. There are more than 50 nodes that are vulnerable to this kind of problem, and some of them were just mining during our test. Our analysis system is also deployed on NEO blockchain. Our lab has exclusively disclosed the attack on December of last year. The attack barriers captured by our honeypot are shown as the picture. The node detector is implemented by analyzing and imitating the NEO's P2P protocol, which successfully detected all the nodes in the NEO network. Our victim detector has found more than 13% of NEO nodes are under threat of remote RPC attack. In conclusion, the RPC attacks in different blockchain projects have similarities. The analysis system we shared here is put for all of them.
Next, let's look at an example of Ethereum's P2P Discover protocol. The problem occurred in the Ethereum P2P Discover protocol when checking the topic register packets. The IDX field of the packet is defined as unsigned integer type, which is not converted to integer when checked, resulting in check failure and overflow access. Attackers can modify the client code, call the sendTopic_register function to set IDX to +1. It will cause remote DOS to the target node. The fix for this bug is as simple as converting IDX to integer. This is an example of Ethereum's P2P synchronization protocol. This problem occurs in the synchronization protocol of Ethereum Light node when processing get block header message. As shown in the figure, the skip field of the packet is controllable by attacker, and there is no check for integer overflow when it +1. This leads to out-of-bounds access. An attacker can modify the client and send a get block header message that sets the skip field to +1. It will cause the target node's DOS. This is a case of NOT's P2P consensus protocol. This problem occurs in the DBFT consensus protocol in ONT when processing prepare request message. As shown in the figure, it creates an array by length. However, the length is controllable by attacker, and there is no check for its value. This leads to out of memory. An attacker can modify the client and send a prepare request message that sets the length field to +1. It will cause the target node's DOS.
This vulnerability has a CVE number. The vulnerable program Bitcoin Core is a popular client of Bitcoin. The vulnerability exists in the transaction validation process of a newly received block. As shown in this picture, when the function check transaction is called with the third parameter set to true, it will enable the check for duplicate inputs within a transaction. However, this check is very time-consuming. Therefore, developers have disabled it because they believed that the detailed transaction handling code could take good care of this kind of unusual situation. Unfortunately, it didn't. Attackers can leverage a malformed block to kiss the crash of normal nodes or successfully double-spend his balance. To achieve the DOS attack, transaction 2 is forked to contain transaction 1 as an input twice. In this attack, transaction 1 and transaction 2 is recorded in the same block. And if transaction 1 is recorded in a previous block, transaction 2 will not kiss a DOS. Instead, other vulnerable nodes will believe that transaction 2 is valid, which will result in the double spend problem. Here is another vulnerability. It exists in the smart contract interpreting process of NEO nodes. Its smart contract is in the format of WASL. When a new smart contract is deployed on the network, nodes will parse and interpret its bytecodes. Vulnerability exists in the interpreting process. At location 1, the vulnerable variable offset is an attacker controllable integer. Before fix, the value of offset is validated to prevent integer overflow using assert function. However, assert is not applicable for non-debug version. Therefore, the local variable table will be leveraged to implement out-of-bound write at location 3. To exploit this vulnerability, we can overwrite another model's opcode and then invoke this model to do attribute memory read and write. This is a problem that occurs in the smart contract API for US.
The function of the API is to calculate a multiplication. It has an error checking for overflow. This problem is very subtle. And shown in the figure, this check is implemented from the source code. However, when compared to WSM, the assert check is optimized. Therefore, the overflow check fails.
Now let's make a conclusion. The increasing market value of digital concurrencies has attracted lots of attackers' attention on blockchain security. As a new technique, blockchain projects have exposed different kinds of attack surfaces. These attack surfaces have been found to have real security problems, even attack events. While blockchain technology is being applied in more and more industry fields, new security problems will bring more serious threat and harm. Therefore, making more in-depth study on the blockchain security is very important in the future. Okay, that's all. Thank you.
Thank you very much for your presentation. Now, if there is any question, you can just raise your hand and I will give you the mic. No question, I'm not sure. Okay, thank you again. And
thank you.
Nice.